All right, so getting into the actual definition here for a um, recursive sequence. We've already touched on, already talked about it a little bit, but again, the more formal definition, we say that a recursively defined sequence, it has to have two parts. Okay, number one, we have to be given the first term, and then number two, we have to have that definition that describes how we're going to get the upcoming terms. So in class initially, again, second period, we asked for a couple of values. Kelsey told us that we should start with the number 4, and then Olivia told us that we should add 7 to every term. So knowing that we're going to add 7 to the next term, that's how we went from 4 to 11. Adding 7 to that next term is how we would get to 18. Adding 7 to that next term is how we would get to 25, and that pattern would go as long as we would like it to. But again, we have to know that first term was 4, and we had to know that the plan was that we were going to add 7 to the current term to get the next term. If we're missing one of those parts, recursive definition just literally falls apart. Again, imagine that we only had the first part to where Kelsey told us that we start at 4, but we didn't know how to get to the second term. Then I guess we would stop at 4. Like literally, we'd have nowhere to go. Or also, if Olivia told us that we're going to add 7 to each term to get to the next, if we don't know where we're beginning, then we can't be nearly as successful as we could or should be. So please understand that the recursive definition, we definitely need both parts. So for students in past years, and I would anticipate, again, just having gone through this with second period so far, for the most part, students understand how to do the recursive definition, how to start with a specific value and then do, for lack of a better way of saying it, to do some math and get to the second term, and do the same math and get to the third term, and do the same math and get to the fourth term, and so on. We understand that part we're good with. It's the notation that throws us off. It looks a little weird here in our example, as you can see. It says to find the first 4 terms of or for the recursively defined sequence, given as a sub 1 is 15, easy enough. But then where it starts to look a little weird is a sub k plus 1 is equal to a sub k plus 3. Now, understand, please, that all that that's saying is that to get the next term, we are going to say that that's equal to our current term plus 3. So I think what is going to help significantly is if we were to think about a sub k. A sub k, because we are trying to speak in generalities. We're trying to be very, very generic on purpose, because we know that we don't always have to start at the first term. You could start at the 5th term. You could start at the 11th term. You could start at the 2000th term. But what we're saying here is that we're starting at a sub k. Okay? We don't know if it's the 1st, 5th, 4th, 2000th, whatever. We just don't know. So it's going to be a sub k. But if our task was to figure out, all right, well, if this is where we are, what's the next term? The best we can say is a sub k plus 1. Because if k is equal to 1, then k plus 1, 1 plus 1 would be 2. So we would think about that as literally being, if this is a sub 1, then next we would go to a sub 2, because 1 plus 1 is how we obtain 2. If k was, what did we say before, 2000, then that's a sub 2000. Well, then this is just going to be a sub k plus 1. That's going to be a sub 2001. All that k plus 1 means, all that is signifying, is that that's the next term. That's the next term that comes after k. Now, again, this is the way that it's typically generally going to be written. But if we wanted to look at a sub k and think, well, what comes before that? I guess technically a sub k minus 1 is the term that is going to come before that. So if a sub k is the 8th term, then k minus 1, 8 minus 1, oh, I guess the 7th term comes before it, which should come as absolutely no surprise whatsoever. It's just the notation is what typically messes with you. All right, so back to our example. We are told that the first term is 15, and we want to find the first 4 terms. So again, the first term is 15. There it goes, sorry, a bit of a delay. So the first, second, third, fourth terms, and once again, we do know that that first term is 15. So all that this is saying is if that is a sub k, then a sub k plus 1 is literally going to be a sub k, which is our 15, plus 3, I guess that's going to be 18. Now, from here, everything shifts. Now a sub k is this term. Again, a sub k, for our purposes, just represents our current term. So right now, our current term, the one that we just found, is our second, a sub 2. So our next term is going to be a sub k plus 1, or in this case, our third term. So all we're going to do is take our current term of 18 plus 3 more to get 21. Now our current term is 21 plus 3, we get 24. That pattern would definitely continue, but all that we are asked to do is find the first 4. Okay. So again, the notation looks a little funny, but again, the actual math behind this is not so bad. So example number 4, you can find this on page 608. Again, this one, more subscripts that potentially could throw some people off. Hopefully not, though. When looking at this, we're given that a sub 1 is equal to 3. But this time, my definition, we're told that a sub k is equal to 2 times a sub k minus 1 plus 1. So what that means is that to find the current term, we have to look at the previous term. So again, a sub k, if we refer to that as the current term, then a sub k minus 1 is going to be the previous term. And going back to the last problem, you won't see it in this one, but if we had a sub k plus 1, then that's what we refer to as the next term. All right, so again, I know that this is asking a lot, but please just don't make it harder than it has to be. Again, 99% of the time when students struggle with recursive definitions, it's literally we're making it too hard. We're making it harder than we need to, okay? So we're asked to write out the first 5 terms. So we have our first, second, third, fourth, and fifth terms. And we are just handed that a sub 1. My first term is 3. All right. So now to find the second term, we're going to allow k to equal 2 because I'm trying to find the second term. Well, if k equals 2, then when I look back over here, k equals 2, 2 minus 1 here. Oh, I guess all I'm really doing is 2 times a sub 1 plus 1. We know what a sub 1 is in this problem, don't we? We know that a sub 1 is 3. So the math that we're really doing is 2 times my previous term plus 1 is going to give us the current term. So if the previous term was 3, 2 times 3, 6 plus 1 tells us that my second term is now 7. All right, now everything shifts, sort of. Now my current term, what we're targeting here is 3. The way that we're going to find the third term is to plug in the previous, or the second term, which we found to be 7. 2 times 7 is 14, plus 1 is 15. It changes again. Now we're finding our fourth term, which means that we better plug our third term in place, double it, and add 1. 2 times 15, 30, plus 1 is 31. Finally, for the fifth term, we can find this. We can obtain this by plugging in our fourth term. 2 times 31 is 62, plus 1 more is 63. If we needed to find the first 5 terms, there they are. Once again, doing the recursive definition is usually not the hard part. Sifting through all of the subscripts and all this other garbage and the notation, that's usually what people struggle with. Again, it's really a mindset we're going to decide right now that, all right, I'm not going to get tricked by that. All right, so we went through this in class. So it's a bit of a math joke. Not everybody thinks they're funny. I understand that. But if we're looking at this, 230 minus 220 times 5 equals what? And we say, you probably won't believe it, but the answer is, so this is a play on the order of operations and mathematical symbols. So most people would do this and say, all right, 220 times 0.5, that's going to be 110. 230 minus 110, and we're obtaining 120. And then a lot of people read this as, but the answer is 5. Well, guys, understand, please, we're not really excited about the number 5. We're giving you a symbol. we're telling you that, believe it or not, the answer is 5 factorial. So that's the whole joke here, is to recognize that 5 factorial is really 5 times 4 times 3 times 2 times 1. That's what factorials do, is they take the value and multiply by every integer until you get down to 1. So in this particular case, 5 factorial, or 5 times 4 times 3 times 2 times 1, is 120. So when you originally looked at this and you saw the 120, you were right. It's just that that's equivalent to 5 factorial. All right, so the reason why we bring that joke in is that we need to talk about factorial. So by definition, we say that if n is a positive integer, n factorial is defined as, and as you can see, there is our formal definition. Like I said in class today, I think pretty much every other math teacher, is going to prefer to see it the other way, to where we're basically in reverse, to where we want to start with n and multiply by the all preceding values. So basically, we would just flip that around. As you know, though, multiplication is commutative, so it really doesn't matter. It's more personal preference. All right, there is a special case. 0 factorial is equal to 1. We can do this on a graphing calculator, or scientific for that matter. On a graphing calculator, you want to find that math button, scroll over to PRB. Your fourth option down is going to have the factorial symbol. If you are using a scientific calculator, you should be able to locate that PRB button. Let's see, where is it located? If you were to find if you're using the type that I have in class, Texas Instrument, the TI-32X, or the TI-30X2S, if you were to locate the 7 and go up 4 buttons, there's your PRB. All right, so we already did this first one. 5 factorial, again, is going to be 5 times 4 times 3 times 2 times 1, which is 120. We can make it look a little bit more complicated, of course. If we had 8 factorial over 2 factorial times 6 factorial, the 8 factorial in the numerator, again, 8, 7, 6, 5, 4, 3, 2, 1, over my denominator of, well, we have 2 factorial, so 2 times 1 times 6 factorial, 6, 5, 4, 3, 2, 1. I'm sure that you're sitting there with the answer saying, like, why is this guy wasting all this time to write it out? I just want to showcase the fact that when you're dividing factorials, there's going to be a lot of opportunities for cancellations to occur. So the 6s, 5s, 4s, 3s, 2s, and because I like crossing stuff out, we'll even say the 1s, they all cancel out. We could also reduce the 2 here and refer to this numerator as 4 times 7, which is going to be 20. This is, I'm sure, the exact same value that you obtained on your calculator, a whole lot faster, but we want to show that that's how this works. All right, next up, what we want to talk about is a series. Again, we already talked about, again, the differences between sequences and series, and again, only half-jokingly said that the truest difference is that a sequence, you're going to list out the numbers and put commas between the numbers. But for a series, you're going to put addition signs, plus signs, and actually add them at the end. That I say it half jokingly because there's a lot of truth to it. That's essentially what you're doing. So for the definition of a series, we just say it's the sum of a sequence. Again, the majority of our work is going to look very similar. We have to find the elements that are in that sequence. It's just at the end, we add them up. Okay, so one of the things that we're going to be utilizing, a convenient way of writing this, we refer to as summation notation, or you'll also, I'm sure, have heard of this written as sigma notation. Sigma notation is going to have 4 parts. First, you're going to have what we call the index. Again, index, that word starts with an I, so more often than not, that little variable that we'll use is an I, but it doesn't have to be an I. It could be a K, could be R, could be X, could be N, could be whatever, really. But I would say more often than not, it's going to be I for index. Whatever this is equal to, that's what we refer to as the lower limit of the summation. Basically, that tells you which term to start with. So here, if we are saying I equals 1, we're literally going to start, start with the first term. If we said that I was equal to 7, we would start with the 7th term. Again, we could start wherever we want. In this case, the value that's up here, we're going generic, calling it n. That's the upper limit. That tells us which term to stop with. So if we said that I is equal to 1 as the lower limit going to the 5th term, then we would be adding up the 1st, 2nd, 3rd, 4th, and 5th terms. But if n were, that upper limit were 100, then we would have to add up the first 100 terms. All right, then the last thing that you're going to see is some sort of a definition. how do I go from, like, how do I find the values? All right, but that's your summation notation.